This is section 10.3, Polynomial and Rational Functions. This is the formal definition of a polynomial function. That's not anything you have to memorize, but what you're more used to seeing is something like y equals x cubed plus 4x squared plus 2x minus 5. So this string of expressions, terms, with exponents. The exponent, here's the important part, an exponent in a polynomial function cannot be a radical, a fraction, or negative. If it's any of those things, it ceases to be polynomial. So that's something to remember. Let me get rid of this. So let's talk about turning points in a polynomial function. Those occur whenever the graph changes from increasing to decreasing or vice versa. So when you're decreasing, and you hit a point and then now you're increasing, that's a minimum. It is called a turning point. If you're increasing, you hit a point, now you're decreasing, that is a maximum. So that's something to remember, that term, turning point. Okay. Now, let's talk about several different kinds of polynomial functions that they have other names, but they're still polynomial. So constant function, remember that's f of x equals a, or say y equals 2, y equals any number. It's a horizontal line, has no x-intercepts and no turning points. It's just a straight horizontal line. All right, linear functions are of the form ax plus b. So this is a linear function where a is positive, so that's a positive slope. This is negative. It has one x-intercept and no turning points. Quadratic, ax squared plus bx plus c, and it has one turning point. No matter where, we've got one turning point. And what we do notice is that you could have no x-intercepts, doesn't hit the x-axis, you could have 1, or you could hit 2. So you have those possibilities. Cubic, where the highest degree is 3. You're going to have possibly 2 turning points, no turning points, or 2 in this case. Now, you could have 3 x-intercepts, 1, or 2. So this guy could do several things. Okay. Quartic, that's a 4th degree. Same idea. How many turning points do we have? 1, 2, 3. We could have 4 x-intercepts, 2 x-intercepts. There's one here and here. Or 3 x-intercepts. 1, 2, 3. And 3 turning points. So lots of options there. What we should gather from looking at those different ones, the graph of a polynomial function of degree n, so no matter what the degree is, with n being more than 1, at least 1 or more, has at most n x-intercepts. So what we found, 4th degree could have at most 4 x-intercepts. Those were 1, 2, 3, 4. We could have at most the number of the degrees, so 3, 2. At most we could have 2. Right here we had 2. So that's something to remember. And at most n minus 1 turning points. So if you have a 4th degree, you're going to have at most 3 turning points. If you have a 3rd degree, at most you're going to have 2 turning points. So that's just something to remember and keep in mind. End behavior of polynomial functions, this is a good little chart to have. If it's an even degree, so 2nd, 4th, 6th, if it's even, it's going to, and a is positive, so the leading coefficient is positive, it's going to go up on both ends, up on the left, up on the right. If it's a is negative, it's going to go down on both ends. If it's an odd degree, 1, 3, 5, if a is positive, it goes down on the left, up on the right. A is negative, up on the left, down on the right. We don't use that quite as much these days because we have calculators. When I learned it back in the dark ages, we had to kind of figure out what our graph was going to look like, and that was one of the things that we used to help determine that. All right, a rational function is when you have one polynomial over another one. So it looks like a fraction usually, and they both have to be polynomials. Asymptotes. When we have some boundaries that occur in our rational functions, we have asymptotes, and we have vertical ones and we have horizontal ones. Let's look here. So this yellow part is what the graph actually is. This dotted line is our vertical asymptote. It occurs at x equals 2. And so this function right here, this is what the graph is, y equals 1 over x minus 2. The reason we have this boundary here and it's not part of the graph, x can't be 2. That would give us 0 on the bottom of a fraction, and that's not allowed. So the graph is coming along, gets toward 2 and says I can't live there, I have to go down. Same way here. So that's a boundary. All right. This is how you find vertical or horizontal asymptotes. To find the vertical one, you're going to take that denominator, set it equal to 0, and you'll get your vertical one. Horizontal has a little bit more to it. You look at the degree of the numerator and the degree of the denominator. If the degree of the numerator is less than the denominator, then y equals 0 is a horizontal asymptote. If the degrees are equal, then y equals a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. If the numerator is greater than the denominator degree, then there are no horizontal asymptotes. So let's look at an example of finding these. So if you were asked to graph y equals 3x plus 2 over 2x plus 4, you need to first find both asymptotes. So we take the bottom, set it equal to 0, and solve it and get x equals negative 2. For the horizontal, the degree of the top is 1, the degree of the bottom is 1. They're understood. We don't have those written there, but we know there's an understood 1 right there. So we take the leading coefficient over that one, so y equals 3 over 2. We sketch those dotted lines, x equals negative 2, y equals 1.5. Then we go to the calculator and we put in 3x plus 2 in parentheses divided by 2x plus 4. We get this as our graph. So we know, we already have the boundaries, we know where we're going, and we just fill in the pieces from our calculator. So that's how we would do that if we were doing it by hand but using the calculator to help. So I think that'll get us on the notes. Let's go look at our problems. Alright, so number 1 says graph the function f of x equals x plus 4 squared minus 3. That's a translation that we're going to do. We've learned a little bit about that. And so we know that typically our graph would be right here. Left 4 because it's positive inside the parentheses, and down 3. So move that vertex and move it here. All right. Now with graphing x cubed minus 3x minus 5, we can use our calculator and we can simply put that in and see if we can get a graph. We'll do one of those together. Get my calculator up here. So we'll go to y equals and clear that out, and we'll have an x to the third minus 3x minus 5. And let's see, if we really want this to look like this, we can look at the window. Let's see what we get if we just hit a zoom 6. Okay, you can tell, I think, that that's what it is, that it is this graph here. But if we wanted to really match it, let's change our window. we have negative 10 and 10, but on the y min and max we have hundreds. So let's go down. So we have negative 100 and positive 100, and looks like a scale of 10 on that y scale, each hash mark being 10. So let's see what that looks like. Okay, so here's the deal. That's what I wanted you to see. You could probably pick the correct graph without changing the window, but if you notice, when I changed the y min and max and I changed the scale, noting that every hash was 10, then I got one that looked very much like that. So that's what you should do there. On number 3, you want to be careful. This has a minus in there, and when you do that on your calculator, remember that it is, it is, I keep doing that, this baby negative down here, not the subtraction for that one when it's at the beginning. That's what you want to do, and you should get that. Same thing for number 4. You're just doing those in the calculator. Alright, now number 5 is a rational function. Just be sure if you're doing those on the calculator, which you should, that you want to put the top and bottom in parentheses. That will eliminate the calculator doing some weird things. And check the graphs. These are all 6s on the window, but I think you'll probably be able to see that without changing the window. Alright, number 6. This is a polynomial function. Give the possible values for the degree of the polynomial and give the sign plus or minus for the nth term, the x to the nth term. Alright, so how many turning points do we have? We have 1, 2, 3. And so remember, the degree, the turning points was 1 less than the degree. So we have a 4th degree polynomial. And because it's going up on both left and right, then we have a positive leading coefficient. Number 7, we're finding the vertical and horizontal asymptotes, and we're graphing it. So to find the vertical, take that bottom part, set it equal to 0. We get x equals 4. The x equals is already here, so you can just put the 4 in. Horizontal, the degree of the top is 0, degree of the bottom is 1. And since n is less than m, and I've let the degree be n for the top and m for the bottom, that's the way we did it in college algebra, so I followed here with that. So that means y equals 0 is the horizontal asymptote. Then if you put that in the calculator, you get this graph. X equals 4, let's see. Okay, when I started looking at that, I started noticing that that wasn't correct. This, let me fix this. Okay, that plus did not come out on the print. That should be a plus. So that becomes x plus 4 equals 0. So x is a negative 4, which then actually fits with the graph. I just missed that. So be careful if you're looking. It should be clear on your computer though. Alright, so let's move on to number 8. Alright, again, the vertical asymptote, we take 5 plus 2x equals 0. 2x is negative 5, so x is negative 5 halves. And then same thing with the horizontal, we get y equals 0. X equals negative 5 halves, y equals 0 is there. That is the graph of that one. Number 9. Our vertical asymptote is x equals 4. Horizontal, the degrees are the same, top and bottom, so we look to the leading coefficient, so that would be y equals 1. And so we have this here, looks like our graph, but you could put it in the calculator and verify that for sure. Number 10. Alright, number 10, you have to be careful if you have this situation. You want to go ahead and factor the top and make sure that you don't end up with this. So we had the same factor top and bottom. We could eliminate that so we have no vertical asymptote. be sure that you do that. That would be important. The horizontal asymptote degree on the top is 2. The bottom is 1. Since n is greater, we have no horizontal asymptote. And you end up getting this straight line that happens to have a hole where x is -4. We call that a discontinuity, but it's a removable one because we could factor that and cancel 1 out. So I think that's all the problems for that, and hopefully that will take care of 10.3.